Hello everyone, my name is Anthony Shivkumar, and in this video we're going to do an introduction to GCC. Now you might say, why do we want to learn about GCC? Now when it comes to embedded systems, whether I'm programming the MCU Expresso, whether I'm using the MCU Expresso to program any NXP microcontroller, or whether I'm using to program, say, the Arduino, in this particular case, say using, it used to be called Atmel Studio, Microchip bought Atmel, and now it's called Microchip Studio, though it's exactly the same interface. They all tend to use GCC. Now, Microchip does have their own compiler as well. But my point is, if you want to understand how to compile, say, embedded systems, you can basically start to use GCC, and understanding how it works can really help you understand what the compilation errors are, how do you want to link certain files, or if you want to use and compile for your embedded systems using a command line. These things can help. All right. So, for example, when you go to, say, the Microchip information, they have the capability of they have the ability for you to program either in MP Labs or in or using the GCC compiler, and the same thing for MCU Expresso. Now, the MCU Expresso, for example, if I come over here and if I'm programming, say, for one of my microcontrollers over here, and I click, say, the build function, what's really happening under the hood? It's taking a makefile and it's compiling it into, say, the executable. And the compiler that it's using is compiling something. What is it compiling, right? It's compiling my source file. But what is the compiler used, and why do I need to compile my code? Because it's taking the C program or high-level program and compiling it into, say, machine code so that I can run on a microcontroller or any processor for the matter of fact, and that can be executable. Now, in this particular case, I've not touched any files. So for this page, let me show you how it actually works. So I can go to my source file over here. And we'll go to SPI.net, SPI.c, which is a protocol that I was working with. Command. Just to make some changes. If you don't make any changes, it may not compile. I'm just going to put this in here, and then let's say build. As you can see, it's taken something and it's doing something, right? Like, what is it doing? It's trying to say, okay, we're going to take this file. We're going to invoke a compiler, which is called a C compiler. We're going to use the ARM NUN EABI GCC compiler. Now, depending on the target you're programming, you'll have to have a different version of GCC, or a specific version of, not a version, but a different type of GCC, because it's compiling to the ARM processor. So the goal over here is that when you download this particular compiler of GCC, the GCC compiler basically has two aspects to it. It's basically taking your C code and it's compiling it into, say, a machine code, and then there's the next step, which is basically linking all the different source files into an executable. But in this particular case, you wanted to compile into, say, ARM instruction sets, or an x86 instruction set. In this particular case, ARM. So we're using the ARM version of GCC. And that's really the difference between why you need to specify a specific type of GCC, so that it's compiling it into the machine code that can run on that particular processor. So to make sense of all of this, it's good to have an understanding of what GCC is all about. A little bit of the rant, and let's get started. Same over here for Microchip, they use GCC. They have their own, their own compiler as well. But in this particular case, you can also use GCC compiles into C. So what we're going to do is just have a fairly basic introduction of how all these IDEs under the hood is doing something. And let's try to make sense of it by just breaking it down and seeing what is GCC actually doing and how is it compiling the code. All right. So I have an introduction to GCC in my Linux environment. Generally speaking, when I'm doing embedded systems, I do use the IDE provided by the manufacturer. But at times when I'm doing, say, writing programs in C, and for a Linux operating system, that's when I start to, use my, command line in this particular case. So I've just created a program called Introduction to C, or intro.gcc, and there's nothing in here. So the first thing we're going to do is create a main.c file, and we're just going to go and try to compile it. So I'm going to do an hash include stdio.h. We're going to have, say, an int main, and we're just going to say printf hello world, which is the normal common thing. We're going to save the file, and then we're going to compile it. So the first thing you want to do is when you're printing, compiling from the command line, you want to invoke gcc main.c.o. Now, when I look at, say, what my LPC Expresso is doing under the hood, let's see what it's doing. It's also using the compiler, in this particular case, ARM ebaby, none hyphen eabi hyphen gcc. And it's got some parameters in here, and then it's compiling it into, and it's taking my, it has a lot of these options, and we'll try to go into a few of them, not all of them. And then it's basically compiling all the source files. That's exactly what we're doing over here. So to make sense of what you're seeing and to make sense of, how to build a simple main program, we're following the same syntax. And that's what these IDEs do. It's just that they're making it more simpler for you so that you don't write these commands. And here it's compiled into main.c. So now when I run main, it's going to say hello world. Nothing wrong with that. Everything perfect. So now what if I have two files? So now let's create another file called, say, touch.hello.h. And in hello.h, I'm going to have, say, an ash include, and in here, include and stdio.h. I'm also going to have, say, a char is going to give me an output of, say, hello. And I'm going to declare this function over here. All right. And just to open it up, I'm going to basically go to my main.c file, and I am going to include, say, hello.h. Now, the difference between putting brackets and putting, say, inverted commas, in this particular case, I'm putting inverted commas, or quotation marks, is because if I put this symbol, when I'm doing my ash include, is mostly going to check in my system path. But when I put these quotation marks, it's basically going to check for this file within the folder in which I'm compiling. So that's really it. And what I'm going to do is I am going to delete this file. I'm going to click return 0, which I should have done earlier. You know what? I will comment this and I'll tell you why, how you can enable certain forms of error logging or warning error logging soon. So I'm just going to click hello. I'm going to say char string is equals to hello, and we're going to do a printf, and we're going to say %s and s. Okay, so what we're doing is we're taking a function, we're putting it into this pointer because it's returning a pointer, and we're going to basically printf this pointer. Now, we're basically defined this in the hello.h, but we have not defined the function itself. So let's see what happens when we don't define the function and we start to execute it. So we're going to do gcc slash main.c slash o to main. And now it says we've got the compiled, but there's an undefined reference. Now this is where you have a linker problem. It's saying, okay, we've got hello.c, we do not know what the function is. And if you do not know what the function is, you can't execute this function, or you can't execute this particular program. So now let's try to fix that. So what I'm going to do is going to create an hello.c file. And in here, I'm going to define or declare that function. And I'm going to do an hash include hello.h. And in here, I'm going to say char %s hello, char %hello, which is basically a pointer, which is going to return a pointer. And in here, I'm going to define a string, say as s, which is equals to this is a great program. And I'm going to return s. Now when we compile it, so when we're compiling two files, we want to put main.c, and then we also want to put hello.c, and then we're going to output it as main. And now when I run main, we can see that it's now executing. All right. Now, is one thing that I would like to do. If I go to main.c, I would like to basically put a \n so that it's printing in a new line. Now, this is what it's doing when you're compiling a couple of files. So when I look at my MCU Expresso, which is also using GCC in this particular case, you'll see that all the files that are there in my folders, it is somehow including them. It's using all of these files. It's explicitly putting these files in this particular in the syntax, right? So we're trying to make sense of what it's really doing. Now it also has something called as let's put this out here. It's got some include paths, and it has let me see, what else does it have? it has a wall. So what does this do? So let's try to figure out what this does. All right. So I'm going to go over here and I'm going to put a GCC/w all. All right. And let me make an error in this particular case. Main.c. No, not main.c. main.c. And let me not put int. Let me put void. And I'm going to return. And I'm going to return, say 0. Say there's a little bit of an ambiguity in here. I'm saying void, but I'm returning 0. And then I basically put a GCC. And that's what W all does. It's basically saying warning all. So W stands for warning and all means give me all types of warning. And what it's basically saying is that return type of main is not int, but you're returning a value. And in order to fix that, I can basically go to main.c. And just to fix that, I can type in int, and then we should be able to eliminate that error. So that's what W all means. And now when I can execute my program, I'm able to execute this. So when we look at what this compiler is doing, it's creating this wall 3 over here. Now OO stands for optimization, G3 means debug symbols, and then there's also other parameters which are including directories, including path names. Here you're basically saying that these are macros that you want to basically include, saying that this is define this for the Cortex M3 processor. We use the LPC open file, and these are all the hash defined statements that we'll go more into this in maybe in a later video. But for now, let's do one more thing. Let's create a crash dump so that we're introducing a little bit of what could go wrong with the program and how we can make sense of it. So now what we've spoken about how to compile a file, how to link a file, what are warning errors, and now let's make a crash dump. So we're going to go to main.c, and in here I am going to create I'm going to initialize, say, int b is equals to null. And I'm going to dereference int b. So I'm going to say print f %d is a value, something of that sort, \n. And we're going to say b, we're just going to dereference this to b, and we have to what have I done over here? Dereference this to b, and I'm going to initialize this as a pointer. All right, and now I'm going to compile it. And now, as you can see, it compiled fine, nothing wrong. Now let me run this program and see what happens. And then we have a core dump. So though it's compiled, we have an error problem, and the reason being is because we're trying to dereference a null pointer. So now, in order for you to dereference a null pointer, it creates a core file over here. Now, in order to set the core file, you need to basically put ulimit /c, and it will tell you whether it's unlimited. That's basically saying what is the core file maximum file size, and I put it over here in unlimited. Now, if you're using Ubuntu, there is something that you might want to stop. You might want to stop your let me show you what you want to do. You want to stop your apport stop, because sometimes this particular program captures all the source files. So if you're not getting code file to stop, just basically stop this stop this process. And once you stop the process, you should be able to get your core dump onto your local directory. So you got to first put an unlimited C. So you put a ulimit /c, type in unlimited, and then that will basically say the core file can be unlimited size, and then you stop that port. This is mostly for Ubuntu systems. In some versions and flavors of Linux, you may not necessarily have to execute this. But if you're not able to get your core dump files on, try to stop it. Now what we want to do is create a GDB and see where the program error is. So I can put GDB, I'm going to put in main, and I'm going to put in core. And here it says there is no debug symbols found. Interesting. So even if I put a backtrace, it's not able to execute anything. So let's figure out how we can solve this problem. So you want to have your /g over here, because now it's basically created an output file of /g. And now when we look at the file size, you can see that the core file is significantly bigger. The main file is 4 KBs more bigger. And that's because we have added more symbols. We have added symbols to the executable and making it more helping us debug if there's a crash file. Okay, So the syntax of using this is very critical, because where you position the options makes a difference. Because if I position /g after the output parameter, then it's going to create a file called /g. That's what we did over here. So that was the error. And now that we have this, now let's try to run this program ./main, and let's create a core dump. And now let's do a gdb /main, and then let's do core. And now it's able to read the symbols, and it's able to understand where exactly in the address is. It's also able to tell me where exactly the file, where exactly is the program crashing. And that's very important. So if I do a backtrace, it's going to tell me it started in the main function, and in the main function, this is the line number where the issue is. And that's how GDB can really help you when you basically are dealing with, especially when you're dereferencing a null pointer. That's more or less the reason why it would crash. The other reasons why it could crash because it's always related to memory. Maybe there's a memory overflow. Maybe you don't have enough memory and you want to access more memory. But crashes are generally related to memory. And for that matter of fact, because it's related to memory, you want to know what's causing your memory leakage, or dereferencing a null pointer, or maybe buffer overflow, whatever be it. You want to make sure you can dereference and understand what's happening. And that's where GDB is so helpful and so useful. So that's really in a nutshell of introduction to GCC. So what have we learned today? We have learned basically how to compile a GCC code into a simple executable. We have learned how to enable warnings. We have learned how to capture core dumps. We also learned how to link two files together so that you can not just compiling from one file. You're also able to link them and create an executable. And that's all there is for it today. And in the future videos, we'll talk and go a little bit more into details as to how this works. And we also compared it to how IDEs basically abstract all this from you. And it's a good idea to understand how it works, so that if there's an error in your IDE, you know exactly, oh, there's an include file missing. Oh, I want to understand how to, see my core dumps. Let me add the option of /g. Or if I want some optimization parameters, I can, add in some optimization. We won't talk about optimization today, but, making sense of, what's happening in your file and what's printing and spitting out can really make all the difference. We'll also talk a little bit about makefiles in the future video. That's all there is for it right now. If you like this video, subscribe to this video and like this channel. It means a lot to me. Thank you so much.